You are listening to Drift Think. Listen as you drift away into a deep sleep. The stars have always been there. Before cities, before history, before we even had words for them. Humanity has looked up, wondering, what are they? What do they mean? Are they just lights in the sky, or something more? We may never know the thoughts of the very first stargazers, but what we do know is that across cultures, across continents, people have built structures, not to house themselves, but to measure the movements of the heavens. Tonight, as you relax and drift into sleep, let's journey back in time to some of the oldest astronomical observatories in history, places where people stood beneath the same sky as we do, searching for answers. Ancient astronomical observatories. Look around. You're standing in a vast, open field in what is now England. The wind carries across the grass, and in front of you stand massive stones, towering and ancient. This is Stonehenge, built over 4,000 years ago, and while no one knows its full purpose, one thing is clear: it is aligned with the sun. On the summer solstice, the longest day of the year, the sun rises in perfect alignment with the heel stone, casting a dramatic shadow through the monument. But why? Was it a calendar? A sacred space? A tool to predict eclipses? Imagine the people who built it, carefully arranging these massive stones without modern tools, using nothing but their knowledge of the sky. And then, let's travel across the ocean, thousands of miles away, to the dry desert of Peru. Here lies Chanquillo, an ancient complex built over 2,300 years ago. Unlike Stonehenge, this observatory isn't just a few standing stones. It's a full-fledged solar calendar. 13 towers stretch along a ridge, each one marking a different position of the rising and setting sun throughout the year. Imagine standing there, thousands of years ago, watching the sun climb over a specific tower, knowing exactly what season it was. For early civilizations, this wasn't just about curiosity. This was survival. Knowing when to plant, when to harvest, when the seasons would change, it all depended on understanding the sky. But the Mayans took this even further. Deep in the jungles of Mexico, at Chichen Itza, stands El Caracol, an ancient observatory named the Snail because of its spiral shape. Unlike Stonehenge or Chanquillo, which focus mostly on the sun, the Maya were fascinated by Venus. They tracked its movements with astonishing precision, so much so that their calendar predicted Venus's cycle more accurately than early European calendars did. But why Venus? To the Maya, it wasn't just a planet. It was a god, a celestial force that influenced war, agriculture, and even the fate of kings. Imagine a Mayan astronomer standing on top of El Caracol, eyes fixed on the night sky, waiting for Venus to rise, knowing that its position could determine whether or not their civilization went to war. And yet, the Maya were not alone in their devotion to the sky. Half a world away, in China, the Yuan dynasty built the Gaochang Astronomical Observatory in the 13th century. It wasn't built with giant stones or towering ridges, but with precise measuring tools. A 40-foot-tall gnomon used to track the sun's shadow and measure time with astonishing accuracy. This wasn't just an academic pursuit. The Chinese emperor was seen as the son of heaven, and his ability to track the cosmos was directly tied to his legitimacy as a ruler. If he couldn't predict the movements of the heavens correctly, it was seen as a sign that his reign was coming to an end. Imagine the pressure, an entire empire depending on your calculations, knowing that a single mistake could shake the faith of millions. And then, let's travel to Egypt, where a groundbreaking discovery has just been made. In 2024, archaeologists uncovered what could be the oldest known astronomical observatory, hidden within the Buto Temple complex. Built in the 6th century BCE, this structure wasn't just used to track the sun, it was designed to monitor entire celestial cycles. Think about that. More than 2,500 years ago, Egyptian priests were using precise engineering to track the movement of celestial bodies. The same civilization that built the pyramids was also mapping the stars with a level of precision we're only now beginning to fully understand. Why does this matter? Why did ancient civilizations spend so much time and effort building structures to track the heavens? The answer is simple: because the sky was their guide. The sun told them when to plant and when to harvest. The stars told them when to travel. The moon helped them measure time. Every civilization, no matter where they were, looked up at the sky and saw a pattern, a system, a story waiting to be told. And in a way, that hasn't changed. Today, we have computers and telescopes that scan the universe in ways our ancestors could never have imagined. But at its core, the quest remains the same. We still look up. We still wonder. We still seek answers. Maybe that's what makes astronomy so special. It connects us, not just to the universe, but to each other, across time. So as you lie back and drift into sleep, imagine the people who stood at these ancient observatories, watching the sky just as you are now. Imagine the whisper of the wind through Stonehenge, the bright glow of Venus over Chichen Itza, the shadow moving across a sundial in China. They watched, they learned, they dreamed. And in a way, so do we. Babylonian and Egyptian astronomy. For as long as humans have looked up, we've searched for meaning in the stars. The night sky wasn't just a spectacle, it was a map, a calendar, a message from the gods. Some of the earliest civilizations didn't just watch the stars. They measured them, recorded them, and built their societies around their rhythms. Tonight, we travel back to Babylon and ancient Egypt, two of the most advanced astronomical civilizations of their time. What did they see when they looked up? What did they believe? And how did their discoveries shape the world we live in today? The Babylonian Sky Watchers. The year is 1800 BCE, and you are standing in Babylon, one of the greatest cities of the ancient world. The streets are lined with grand temples, and above them, the stars shine brightly in the warm desert sky. The Babylonians were obsessed with the heavens, not just in a mystical or religious way, but in a scientific one. They were some of the first people in history to write down detailed records of the night sky, creating star charts, tracking planets, and recording eclipses centuries before the Greeks or Romans even existed. But why? What drove them to spend so much time studying the stars? To them, the sky was a giant clock, a cosmic machine that could predict the future. The Babylonians believed that everything in the heavens had meaning, that the position of the planets and the timing of an eclipse could foretell the fate of kings and empires. They invented the zodiac, dividing the sky into 12 equal sections, each associated with a constellation. If that sounds familiar, it's because we still use their system today. Your astrological sign? That's a Babylonian invention from nearly 4,000 years ago. But their knowledge didn't just stay in Babylon. Their discoveries spread, influencing the Greeks, the Romans, and even modern astronomy. Imagine a Babylonian astronomer standing on the rooftop of a ziggurat, staring at the planets with nothing but the naked eye, carefully recording their positions night after night. They didn't have telescopes. They didn't have computers. Yet, they were able to predict eclipses, track the motions of Venus, and even estimate the length of a year to within a few minutes of modern calculations. They were far ahead of their time. But they weren't alone. While Babylonian astronomers were mapping the sky across the desert, another civilization was aligning their monuments with the heavens: the Egyptians. The Egyptian stargazers. Imagine standing beneath the towering pyramids of Giza, their smooth limestone faces glowing in the moonlight. The Nile flows quietly in the distance, and above you, the stars seem to dance in perfect harmony. To the Egyptians, the sky was not just a tool for measurement. It was divine. The stars represented gods, the sun was a deity, and the afterlife itself was written in the cosmos. But how deep did their knowledge go? Did the Egyptians truly understand astronomy, or was it all just mythology? The evidence suggests both. The pyramids of Giza, for example, are perfectly aligned with the cardinal points: north, south, east, and west. Some researchers believe that the shafts inside the Great Pyramid are aligned with specific stars, such as Orion's belt and Sirius, which played a central role in Egyptian mythology. But their fascination with the sky wasn't just spiritual, it was also practical. The flooding of the Nile, the single most important event in Egyptian agriculture, was predicted by the rising of the star Sirius. When Sirius appeared in the dawn sky just before sunrise, the Egyptians knew that the river would soon rise, bringing life to their fields. They even had astronomical ceilings painted inside tombs and temples, showing the positions of the stars, the movements of the planets, and the phases of the moon. Some of these celestial charts date back over 3,500 years, proving that the Egyptians had a sophisticated understanding of time and space. But perhaps the most exciting discovery happened very recently. In 2024, archaeologists uncovered what could be the world's oldest known astronomical observatory, hidden in the Buto Temple complex in Egypt. This site, dating back to the 6th century BCE, contained stone structures and engravings designed to measure the movement of the sun and stars with incredible precision. Think about that. 1,600 years ago, Egyptian priests were tracking celestial cycles with an accuracy we once thought impossible. They weren't just stargazers. They were scientists, engineers, and visionaries, using the sky to guide their civilization, predict floods, build monuments, and navigate the vast deserts. The legacy of the ancients. Babylon and Egypt, two civilizations, separated by distance, yet both looking up at the same sky, searching for meaning. The Babylonians gave us the first star maps, the zodiac, and the ability to predict celestial events. The Egyptians aligned their temples and pyramids with the cosmos, using the stars to measure time and shape their spiritual beliefs. And in many ways, we are still following in their footsteps. Every time we check our horoscopes, every time we use a 365-day calendar, every time we look up and wonder what's out there, We are continuing the legacy of those first astronomers. Their discoveries didn't stay locked in the past. They shaped the world we live in today. And maybe, thousands of years from now, someone will look up at the sky, just as we do, and continue the search for answers. The Greek Revolution in Astronomy. For thousands of years, people watched the stars in wonder, but it was the ancient Greeks who dared to ask bigger questions. Instead of simply observing the heavens, they wanted to explain them. What were the stars made of? How far away were they? Was the Earth really the center of the universe? Or could there be something far more incredible waiting to be discovered? These questions, asked over 2,000 years ago, changed the course of history. Tonight, as you relax and drift into sleep, let's explore how Greek thinkers revolutionized our understanding of the cosmos and laid the foundation for modern astronomy. The first scientific theories. It all began with Thales of Miletus, one of the first known Greek philosophers and scientists. Unlike earlier civilizations, which saw the sky as the realm of gods and spirits, Thales believed that the universe could be understood through reason and observation. Imagine him standing on a rocky shore, gazing at the night sky, asking himself, "Is there a pattern here? A law that governs the stars, just like the tides and the changing of the seasons?" Thales proposed that the heavens were not ruled by divine beings, but by natural forces that could be studied and understood. This idea, so radical at the time, became the foundation of scientific thought itself. But if Thales opened the door to rational astronomy, it was Pythagoras who walked through it. You've probably heard of the Pythagorean theorem. But did you know Pythagoras also believed the Earth was a sphere? Unlike many early civilizations, which imagined the Earth as flat, Pythagoras observed that the moon and sun appeared as perfect circles in the sky. He reasoned that if celestial bodies were round, then maybe the Earth was too. And then came Anaxagoras, who made an even bigger claim. The sun is not a god. It is a massive ball of fire. This was shocking in ancient Greece, where the gods were believed to control the universe. But Anaxagoras saw the sun for what it truly was. Not a divine chariot, but a blazing sphere, far larger than the Earth itself. It was a bold idea, one that would eventually get him exiled from Athens. But he was right. And he wasn't the only one beginning to see the universe in a new way. The geocentric model, Earth at the center. One of the most influential Greek astronomers was Eudoxus of Cnidus, who lived in the 4th century BCE. He proposed a model of the universe with the Earth at its center, surrounded by a series of giant, invisible spheres carrying the sun, moon, and stars. This idea, later refined by Aristotle, became known as the geocentric model, and it would dominate astronomy for nearly 2,000 years. To Aristotle and his followers, the universe was perfect, ordered, and symmetrical. The Earth was the unmoving center, and everything revolved around it in a system of crystalline spheres. It was a comforting idea, one that made sense to people who looked up and saw the stars moving across the sky each night. And for centuries, it was accepted as absolute truth. But not everyone was convinced. The heliocentric model, a sun-centered universe. Enter Aristarchus of Samos, a revolutionary thinker who dared to suggest something unthinkable. What if the Earth isn't the center of the universe? What if the sun is? Unlike Aristotle, Aristarchus proposed a heliocentric model, a system where the Earth and planets revolved around the Sun. Think about how radical that was. For centuries, people believed the Earth was the fixed center of existence. But Aristarchus realized that if the Sun were much larger than the Earth, it made more sense for Earth to orbit it, rather than the other way around. But there was a problem. In Aristarchus's time, there was no telescope to prove this idea. People looked at the sky and saw no visible motion of the Earth. If the Earth was truly moving, shouldn't we be able to feel it? Shouldn't the stars appear to shift as we moved? With no way to prove his theory, Aristarchus's idea was dismissed, and the geocentric model of Aristotle and Ptolemy would continue to dominate astronomy. It would take nearly 1,800 years before another astronomer, Nicholas Copernicus, would revive Aristarchus's theory and prove him right. But even though his idea was rejected at the time, Aristarchus had planted the seed of a revolution, the legacy of Greek astronomy. The ancient Greeks may not have had telescopes or satellites, but their ideas shaped everything that came after them. They were the first to believe that the universe could be understood through reason, observation, and mathematics. They questioned the nature of the stars, the motion of the planets, and the structure of the cosmos, and they passed that knowledge down through the generations. Their work influenced the Romans, the Islamic Golden Age, and eventually the Renaissance, leading to the birth of modern astronomy as we know it today. The Greeks may not have had all the answers, but they asked the right questions. And that's where all great discoveries begin: the Ptolemaic system and its influence. For centuries, humanity looked to the stars and saw a perfect, orderly cosmos, a place where the heavens moved according to divine or mathematical laws. But how exactly did they move? Tonight, we step into the mind of Claudius Ptolemy, the astronomer whose vision of the universe would dominate science for nearly 1,500 years. His ideas shaped not only astronomy, but also philosophy, religion, and even the way we saw ourselves in the cosmos. How did one man's model become the ultimate authority on how the universe worked? And why did it take so long to prove it wrong? The Earth at the center of everything. The year is 150 CE, and you are in Alexandria, Egypt, the greatest center of learning in the ancient world. Inside the Grand Library of Alexandria, scholars from all over the world debate philosophy, medicine, and the mysteries of the cosmos. Among them is Claudius Ptolemy, a Greek-Egyptian astronomer, mathematician, and geographer. He looks up at the night sky and, like everyone before him, sees the stars moving across the heavens, the sun rising and setting, and the planets wandering in strange, looping patterns. To Ptolemy, there is only one logical conclusion. The Earth is at the center of the universe. Everything else, the moon, the sun, the planets, the stars, must revolve around us. This wasn't just a casual guess. Ptolemy built an incredibly detailed mathematical system to explain how the planets moved. His masterpiece, the Almagest, became the definitive astronomical text for over 1,000 years. But there was a problem. If the planets simply orbited Earth in perfect circles, their movements should have been predictable and smooth. Instead, ancient astronomers noticed something strange. Mars sometimes appeared to move backward in the sky before resuming its normal path. Venus and Mercury never strayed far from the Sun, unlike the other planets. The brightness of the planets changed unpredictably, suggesting that their distances weren't constant. To account for these oddities, Ptolemy introduced a concept that would define astronomy for centuries: epicycles. The illusion of epicycles. Imagine looking up at the sky and seeing Mars drifting slowly through the constellations. But then, instead of continuing forward, it pauses, moves backward for a while, and then resumes its normal course. This is called retrograde motion, and it puzzled ancient astronomers for centuries. If all planets moved in perfect circles around Earth, why would one suddenly reverse direction? Ptolemy's solution was epicycles, small circular orbits within a planet's main orbit. In his model, a planet moves along a small circle, the epicycle, while that entire small circle moves along a larger circle around Earth, the deferent. To the observer on Earth, this made it appear as though the planet was moving backward before continuing forward again. It was a brilliant mathematical trick, and for centuries it worked. Ptolemy's model accurately predicted planetary positions, allowing astronomers and astrologers to chart the stars with astonishing precision. But there was one major flaw. The real reason planets appeared to move backward was because Earth itself was moving, something Ptolemy's geocentric model did not account for. His system was built on the wrong assumption, but because it made accurate predictions, people believed it for centuries. The authority of the Ptolemaic system. Ptolemy's model wasn't just an idea, it became law. For over 1,000 years, the Ptolemaic system was taught as absolute truth in the Islamic world, medieval Europe, and beyond. It aligned perfectly with religious doctrine, especially in Christianity and Islam, where the idea of Earth as the center of creation fit naturally with theological beliefs. It also had political power. Rulers and priests used Ptolemy's model to legitimize their authority, connecting the motion of the heavens to the will of the divine. If the universe was a perfect, orderly system with Earth at its center, then the kings, emperors, and religious leaders who ruled it were chosen to do so. To challenge Ptolemy's system wasn't just to challenge astronomy, it was to challenge entire world views. For 1,000 years, no one dared to ask, what if we were wrong? The beginning of the end. But cracks in Ptolemy's system began to appear. By the 15th century, astronomers noticed that the model wasn't as accurate as before. The positions of the planets didn't quite match up with predictions, and new measurements revealed small but undeniable errors. To fix the discrepancies, scholars added more and more epicycles, turning the system into an overly complicated mess of overlapping circles. Some began to ask, what if the entire foundation was wrong? And in the 16th century, a Polish astronomer named Nicholas Copernicus proposed a revolutionary idea. Maybe it's not the planets that are moving strangely. Maybe it's us. His model, placing the sun at the center instead of Earth, would eventually destroy the Ptolemaic system. But even then, it would take another 100 years before the world finally let go of the idea that Earth was the center of everything. The legacy of Ptolemy. Ptolemy's system may have been wrong, but it was a crucial step forward. His work in mathematical astronomy, mapping the stars, and predicting planetary motion helped pave the way for future discoveries. His model lasted not because it was true, but because it was useful, a reminder that even incorrect ideas can help move science forward. Today, We know that planets move in elliptical orbits, that space is vast and ever-expanding, and that Earth is just a small speck in an infinite cosmos. But none of that knowledge would have been possible without the system that came before. Ptolemy's model wasn't the end of the journey. It was just one stop along the way. And as we continue searching the stars, we'll always look back at the past, remembering the ideas that brought us here. Islamic Golden Age astronomy and its contributions. For centuries, the stars have been our guide. They told our ancestors when to plant crops, when to travel, and even how to navigate vast, uncharted oceans. But during the Islamic Golden Age, astronomy became more than just practical knowledge. It became a science. From the 8th to the 14th century, scholars across the Islamic world revolutionized astronomy. They built observatories, designed new mathematical models, and preserved ancient Greek and Roman texts, ensuring that knowledge from the past was not lost, but expanded upon. Tonight, as you relax and drift into sleep, let's explore the incredible contributions of Islamic astronomers, discoveries that shaped the way we understand the universe today. A new era of knowledge. Imagine walking through the grand house of wisdom in Baghdad during the 9th century. The air is filled with the sounds of scribes copying manuscripts, scholars debating complex theories, and astronomers carefully recording the movements of the stars. This was a time when the Islamic world became a center of learning, where knowledge from Greece, Persia, India, and Rome was gathered, translated, and expanded upon. Astronomers of the Islamic Golden Age didn't just accept the teachings of Aristotle and Ptolemy, they challenged and improved them. One of the most important figures of this era was al-Battani, a 9th century astronomer who refined Ptolemy's measurements of the sun and moon. Using careful calculations, he determined the length of a year with astonishing accuracy. His estimate was only minutes off from modern calculations. Think about that. Over 1,000 years ago, without telescopes or computers, al-Battani was able to measure the length of a year with near-perfect precision. But he wasn't alone. Across the Islamic world, from Cordoba to Samarkand, scholars were redefining what was possible in astronomy. The first observatories. While earlier civilizations observed the stars, Islamic astronomers were among the first to build observatories specifically for scientific research. One of the most famous was the Marageh Observatory in present-day Iran, built in the 13th century by Nasir al-Din al-Tusi. This massive research center wasn't just a place for stargazing, it was a think tank, where scholars from all over the world worked together to refine astronomical models. Al-Tusi introduced a mathematical technique known as the Tusi couple, a geometric model that helped explain planetary motion without relying on Ptolemy's complicated epicycles. His work directly influenced Copernicus, who would later use similar techniques in developing the heliocentric model. Another great observatory was the Ulugh Beg Observatory, built in the 15th century in what is now Uzbekistan. Unlike previous observatories that used small instruments, Ulugh Beg's facility featured a massive sextant, allowing astronomers to make extremely precise measurements of celestial objects. With these new tools, Islamic astronomers were able to measure the positions of thousands of stars with incredible accuracy, refine the understanding of planetary motion, improve timekeeping, and develop more precise astronomical tables. Their discoveries weren't just theoretical, they had real-world applications. Astronomy and timekeeping. One of the most practical uses of astronomy during the Islamic Golden Age was timekeeping. For Muslims, knowing the exact time of day was crucial for prayer, fasting, and religious observances. Since Islamic prayers are based on the position of the sun, astronomers developed highly accurate sundials, water clocks, and timekeeping methods. They also perfected the astrolabe, a tool originally developed by the Greeks but vastly improved by Islamic scientists. With an astrolabe, you could determine time based on the stars, find the direction of Mecca from anywhere in the world, navigate at sea with unprecedented precision. It was, in many ways, the first handheld computer, allowing travelers, sailors, and scholars to use the stars as a mathematical guide to the world. And yet, one of the most fascinating contributions of Islamic astronomers was not just about measuring time, but about challenging old ideas, challenging Ptolemy. For centuries, Ptolemy's geocentric model was accepted as fact, but in the Islamic world, astronomers began to question it. One of the first to challenge Ptolemy was Ibn al-Haytham, often called the father of optics. He pointed out flaws in Ptolemy's model, arguing that it was too complex and didn't match real observations. Then came Ibn al-Shatir, a 14th century astronomer in Damascus, who made an incredible breakthrough. He rejected Ptolemy's epicycles. He developed a new mathematical model for planetary motion. His work closely resembled the heliocentric system of Copernicus, 200 years before Copernicus. Did Copernicus borrow ideas from Ibn al-Shatir? Some historians believe so, as Copernicus's planetary models share striking similarities with those developed in the Islamic world. This means that the scientific revolution in Europe, the one that ultimately led to our modern understanding of the cosmos, may have been directly influenced by the discoveries of Islamic astronomers centuries earlier. A lasting impact. The Islamic Golden Age of astronomy was not just about observation, it was about innovation. These scholars preserved, translated, and expanded upon the works of the Greeks and Romans, ensuring that knowledge from the past was not lost. But more importantly, they challenged old ideas and laid the groundwork for new ones. Their research influenced Renaissance astronomers, helped refine navigation, and shaped the way we measure time today. The stars they mapped, the calculations they made, the books they wrote, all of it still echoes in modern astronomy. And though their era has long passed, their discoveries remain, woven into the fabric of how we understand the universe. The same stars they observed still shine above us, and just as they looked up in wonder, so do we. Copernicus and the heliocentric revolution. For centuries, humanity believed that Earth was the center of everything. It was comforting, logical. After all, the sun, moon, and stars all appeared to rise and set around us. But what if we were wrong? What if Earth wasn't the center of the universe at all? Tonight, as you drift into sleep, let's journey back to the 16th century, where one man's ideas would change everything. His name was Nicholas Copernicus, and his theory would shake the very foundation of science, philosophy, and religion. A question no one dared to ask. The year is 1510, and you are in Poland, walking the quiet streets of a cathedral town. In a small, dimly lit room, a man sits at a wooden desk, surrounded by books and astronomical charts. He is deep in thought, scribbling notes by candlelight, staring at the numbers before him. This man is Nicholas Copernicus, a mathematician, astronomer, and, surprisingly, a church official. By day, he works as a canon in the cathedral, fulfilling religious duties. But by night, he is obsessed with a single idea. What if everything we believe about the universe is wrong? For over 1,500 years, the world had followed Ptolemy's geocentric model, which placed Earth at the center of the universe, with the sun, moon, and planets revolving around it. It was a system supported by religion, philosophy, and centuries of observation. But the deeper Copernicus looked, the more he noticed contradictions. Why did the planets move in strange, looping patterns across the sky? Why did the calculated positions of planets sometimes fail to match reality? Why did Ptolemy's model require so many corrections and adjustments? Something didn't add up. Then, one day, Copernicus stumbled upon a radical idea, one that had been suggested long ago but dismissed. What if Earth wasn't at the center at all? What if the sun was? The birth of the heliocentric model. Copernicus realized that if the sun were at the center of the universe, the strange planetary motions suddenly made sense. The retrograde motion of planets, where they appear to move backward in the sky, was just an illusion caused by Earth overtaking them in orbit. The reason Venus and Mercury never strayed far from the sun? Because they orbited the sun, not Earth. The changing brightness of planets? That was simply because their distances from Earth varied as they moved around the sun. It was so elegant, so simple, so obvious, yet so dangerous. This idea, now known as the heliocentric model, meant that Earth was not special. It was just one planet among many, moving through an endless cosmos. But could he prove it? Fear of the Church. Copernicus knew that publishing his theory would be dangerous. At the time, the Catholic Church held enormous power, and questioning the structure of the universe was not just a scientific debate, it was a religious challenge. The Bible itself contained passages that seemed to suggest that Earth was immovable, fixed at the center of creation. To suggest otherwise was to question divine authority. Copernicus hesitated. He spent decades refining his calculations, quietly discussing his ideas with trusted friends. But he refused to publicly release his findings. For nearly 30 years, he kept his manuscript hidden. Finally, in 1543, at the urging of a young mathematician named Georg Joachim Rheticus, Copernicus agreed to publish his life's work on the revolutions of the celestial spheres. But by the time the first copies of his book were printed, Copernicus lay on his deathbed. He never lived to see the chaos his ideas would cause, the backlash. At first, the reaction to Copernicus's work was quiet. His model was seen as an interesting but impractical theory. But then, astronomers began to test it. In the late 1500s, a Danish astronomer named Tycho Brahe made some of the most precise astronomical observations ever recorded. His data, later analyzed by Johannes Kepler, revealed something shocking. Copernicus was right. By the early 1600s, another astronomer, Galileo Galilei, built one of the first powerful telescopes and made a discovery that changed everything. Jupiter had moons orbiting it. If moons could orbit something other than Earth, then Earth could not be the center of the universe. This was proof that Copernicus had been right all along. The Catholic Church, however, did not take this news well. In 1616, the Church officially banned Copernicus's book, declaring the heliocentric model heretical. Galileo, who had publicly defended Copernicus, was put on trial and forced to recant his beliefs under threat of execution. For the Church, the idea that Earth was not the center of everything was too dangerous to accept. But the truth had already been set in motion, the legacy of Copernicus. Though he did not live to see it, Copernicus's theory changed the world forever. It was the beginning of modern astronomy, the first step toward a universe that was far larger and more complex than anyone had imagined. Today, we take it for granted that the Earth orbits the Sun. But in Copernicus's time, this idea was as revolutionary as the discovery of DNA, relativity, or quantum mechanics. His courage to question centuries of accepted truth paved the way for Newton, Einstein, and the space age. And though we now know that even Copernicus's model wasn't completely correct, planets move in ellipses, not perfect circles, his vision of a sun-centered system was the first step toward understanding our place in the cosmos. He redefined our universe. And, perhaps most profoundly, he redefined our place within it. Galileo and the Telescope Revolution. You are listening to Drift Think. Listen as you drift away into a deep sleep. For centuries, the stars seemed distant, untouchable, glowing specks of light in a perfect, unchanging sky. People believed that the heavens were divine, a realm separate from Earth, flawless and eternal. But what if that wasn't true? What if the sky wasn't perfect? What if the moon had craters, Jupiter had moons, and the stars stretched into infinite space? One man dared to look closer than anyone before him. His name was Galileo Galilei, and with a simple telescope, he shattered the way humanity saw the universe. Tonight, as you drift into sleep, let's journey back to 17th century Italy, where one man's discoveries would change everything. A curious mind. The year is 1609, and you are walking through the streets of Venice, Italy. The air is filled with the sounds of merchants, musicians, and the distant waves of the sea. In a small workshop, a middle-aged man with piercing eyes carefully grinds lenses, adjusting them in a long, slender tube. He holds it up to the sky and gasps. This man is Galileo Galilei, and he has just built one of the world's first telescopes. Telescopes were a new invention, originally designed for sailors and merchants to spot ships from far away. But Galileo had a different idea. What if he used this tool to look at the heavens? And so, one night, beneath the clear Italian sky, he turned his telescope toward the moon. What he saw changed everything. The moon wasn't perfect. For centuries, scholars believed that the moon was a flawless celestial sphere, smooth and pure, a divine object hanging in the sky. But Galileo saw something shocking. The moon wasn't smooth at all. It was covered in craters, mountains, and valleys, just like Earth. This was unthinkable. If the heavens were divine and perfect, then why did the moon look broken, rugged, and scarred? Galileo had seen something no human had ever seen before, the imperfections of the cosmos. But this was only the beginning. The moons of Jupiter. One evening in 1610, Galileo turned his telescope toward Jupiter, the largest planet in the sky. He expected to see just a bright point of light, like every astronomer before him. But what he saw was astonishing. Near Jupiter, there were 4 tiny stars lined up in a row, and over the next few nights, they moved. sometimes appearing on one side of Jupiter, sometimes on the other. Galileo realized the truth. They weren't stars. They were moons. Jupiter had its own mini-solar system with moons orbiting around it, just like the Earth and Moon. This discovery was devastating to the old model of the universe. If everything was supposed to revolve around Earth, then why were these moons orbiting Jupiter instead? Galileo's telescope had provided irrefutable proof. Not everything in the cosmos revolved around Earth. It was a direct challenge to the geocentric model, a challenge that would make Galileo very powerful enemies: the rings of Saturn and the phases of Venus. Galileo continued to look deeper into the night sky, and every time he did, he found something new. He observed Saturn's rings, though he couldn't yet understand what they were. He discovered that the Milky Way wasn't just a cloudy band in the sky. It was made of millions of tiny stars, stretching into infinity. And most importantly, he observed the phases of Venus, which could only be explained if Venus was orbiting the Sun, not Earth. This was more proof that the heliocentric model of Copernicus was correct. But proving science right meant proving the Church wrong. And that was dangerous. Galileo versus the Church. In 1616, the Catholic Church banned the heliocentric model, declaring it heretical. The Church's position was clear. Earth was at the center of the universe, and to say otherwise was to defy Scripture. Galileo, now famous for his discoveries, was warned to stop teaching heliocentrism, but he refused. In 1632, he published Dialogue Concerning the Two Chief World Systems, a book that openly mocked the old geocentric model and defended the idea that Earth moved around the Sun. This was too much for the Church. In 1633, Galileo was put on trial for heresy. He was forced to stand before the Inquisition, where he was accused of going against religious doctrine. Faced with imprisonment, or worse, Galileo had no choice. He recanted his views, swearing that Earth did not move. Legend has it that, as he left the courtroom, he whispered under his breath, "And yet, it moves." Galileo was sentenced to house arrest for the rest of his life. But even though the Church silenced him, his ideas could not be erased. The legacy of Galileo. Even under house arrest, Galileo continued his work, writing secretly and passing his ideas to future scientists. He laid the foundation for Isaac Newton's discoveries and helped establish the idea that science should be based on observation and evidence, not authority or tradition. In time, Galileo was proven right. The heliocentric model became universally accepted. His work in physics led to the discovery of gravity. And today, telescopes inspired by his simple design continue to explore the far reaches of the universe. Galileo opened our eyes. He was the first to see the imperfections of the moon, the moons of Jupiter, and the endless expanse of the stars. But more than that, he taught us to question, to observe, and to never stop searching for truth. Because the universe is vast, mysterious, and always waiting to be discovered. Kepler and the laws of planetary motion. For centuries, people believed that the planets moved in perfect circles, tracing elegant paths through the heavens. The universe, they thought, must be orderly, symmetrical, and divine. But what if it wasn't? What if the planets didn't move in perfect circles? What if their paths were stretched, uneven, and dictated by invisible forces? One man figured it out. His name was Johannes Kepler, and with his groundbreaking laws of planetary motion, he revealed the hidden structure of the cosmos. Tonight, as you relax and drift into sleep, let's explore how Kepler unlocked the secrets of planetary movement and how his discoveries paved the way for Newton, Einstein, and modern space travel. A young mind in a changing world. The year is 1600, and you are in Prague, walking through the halls of an observatory where the greatest astronomical data of the time is stored. In one corner, a man sits at a desk, scribbling equations furiously on parchment. His eyes move rapidly between tables of planetary positions and sketches of orbit patterns. His name is Johannes Kepler, and he is about to change everything we know about the motion of the planets. Kepler was born into a world of intellectual upheaval. Copernicus had proposed that the sun, not Earth, was the center of the universe, and Galileo's telescope had provided visual evidence that the old geocentric model was flawed. But there was still a problem. Even in the heliocentric model, astronomers still assumed that planets moved in perfect circles. But what if they didn't? What if the truth was something more complex, more precise, more beautiful? Kepler's mind was restless. He wanted to know the truth, and for that, he needed data, lots of data. And no one had more data than Tycho Brahe, the mentor's observations. Before telescopes, the most detailed astronomical measurements came from the work of Tycho Brahe, a brilliant, eccentric Danish astronomer. Brahe's observatory, Uraniborg, was the most advanced in the world, and his observations of planetary positions were the most precise ever recorded. Brahe himself didn't believe in Copernicus's heliocentric model, but his data, it held the key to proving it. Kepler, eager to solve the mystery of planetary motion, became Brahe's assistant in 1600. For years, he studied Brahe's records, especially the puzzling motion of Mars, which refused to fit into perfect circles. When Brahe died in 1601, Kepler inherited all of his data. Now, with access to the most accurate planetary records in history, he set out to unravel the mystery of the planets once and for all. The first law, elliptical orbits. For centuries, astronomers believed that planets moved in perfect circles around the sun. It seemed logical, even divine. But when Kepler plotted Mars' orbit, something didn't fit. The numbers weren't matching. No matter how hard he tried, the circular model didn't work. And then, it hit him. What if planets didn't move in circles at all? What if their orbits were elliptical, stretched ovals rather than perfect loops? Kepler tested the idea, running the numbers again and again. And finally, the data fit perfectly. The first law of planetary motion was born. The orbit of a planet around the sun is an ellipse, with the sun at one of the focal points. It was a radical idea, one that shattered the old belief that the universe was built on perfect geometric shapes. But Kepler didn't stop there. He wanted to know, how fast do planets move? And the answer was even more surprising. The second law, the speed of planets. Kepler noticed something strange. When Mars was closer to the sun, it moved faster. But when it was farther away, it slowed down. This was shocking because, in ancient astronomy, planets were assumed to move at constant speeds. But Kepler saw the truth. He formulated his second law of planetary motion. A line drawn from the sun to a planet sweeps out equal areas in equal time. This meant that a planet accelerates when closer to the sun and slows down when farther away, something that no one had ever realized before. Kepler had uncovered a fundamental rule of motion, one that would later help Newton formulate the laws of gravity. But he still had one more discovery to make. The third law, a hidden pattern in the cosmos. Kepler had now shown that planets move in ellipses, not circles. They speed up when close to the sun and slow down when far away. But was there a pattern, a mathematical connection between all planetary orbits? Kepler searched, testing every possibility. And then he found it. The time it takes a planet to orbit the sun is directly related to its distance from the sun. This became Kepler's third law of planetary motion. The square of a planet's orbital period is proportional to the cube of its distance from the sun. In simpler terms, this meant that the farther a planet is from the sun, the longer it takes to complete one orbit. This single equation united all planetary motion into one elegant mathematical law, something that astronomers had been searching for since the beginning of time. The legacy of Kepler. Kepler's three laws changed everything. They proved, mathematically, that the heliocentric model was correct. They paved the way for Isaac Newton's theory of gravity, and today, over 400 years later, we still use Kepler's laws to navigate spacecraft through the solar system, calculate planetary orbits around distant stars, search for exoplanets in other galaxies. Kepler revealed the invisible forces shaping the cosmos, and in doing so, he took us one step closer to understanding the vast, mysterious universe we call home. Newton and the law of universal gravitation. For centuries, the motion of the planets was a mystery. Why did they move at all? What force controlled them? Copernicus had placed the sun at the center of the universe, and Kepler had discovered the laws governing planetary motion. But one crucial question remained unanswered. What invisible force kept the planets in their orbits? One man would solve this mystery, a scientist whose discoveries would change not just astronomy, but physics itself. His name was Isaac Newton, and his law of universal gravitation would reveal the force that binds the universe together. The curious child who would change the world. The year is 1665, and you are in England. A young man sits under an apple tree, lost in thought. His name is Isaac Newton, and he has just observed something so simple yet so profound that it will reshape science forever. He watches as an apple falls from the tree, straight to the ground. It's something that happens every day. But Newton asks a question no one else had. Why does the apple fall straight down? Why doesn't it move sideways or float upward? And then he asks an even bigger question. Could the same force pulling the apple down also be pulling the moon around the earth? This single thought, so simple, yet so revolutionary, would lead to one of the greatest discoveries in human history, the birth of universal gravitation. Before Newton, no one understood why planets moved the way they did. Kepler's laws described their motion, but they didn't explain it. Newton realized that the same force that pulls objects to the ground also governs the motion of the planets. He called this force gravity. And then He made an even bolder claim. Gravity isn't just an earthly force. It exists everywhere, acting on everything. This was the key to unlocking the universe. The universal law of gravitation. Newton formulated a simple but profound equation. F equals G, m1, m2. It may look like just a set of symbols, but this equation changed everything. It means that every object in the universe attracts every other object. The strength of this attraction depends on their masses and distance. The greater the mass, the stronger the pull. The farther apart they are, the weaker the force. This equation explained why apples fall, why the moon orbits Earth, why Earth orbits the sun, and even why galaxies stay bound together. For the first time in history, the entire cosmos was governed by a single unifying force. Newton's three laws of motion. To fully describe how objects move, Newton also formulated three fundamental laws that govern all motion in the universe. An object in motion stays in motion unless acted upon by an external force. This means that if something is moving, it will keep moving forever unless something stops it. This is why the planets don't need a constant push. They keep moving in space because there's nothing to slow them down. Force equals mass times acceleration, F equals ma. This law tells us how objects respond when a force is applied. The more massive something is, the more force is needed to move it. For every action, there is an equal and opposite reaction. If you push against a wall, the wall pushes back with equal force. This is why rockets can move in space. They push fuel downward, and the force pushes them upward. These three simple laws, combined with the law of universal gravitation, became the foundation of modern physics. But Newton's discoveries didn't just stay in textbooks. They led to practical, real-world applications that shaped the future of science, technology, and space exploration. Newton's impact on astronomy and space travel. Newton's laws explained everything about planetary motion. For the first time, astronomers could predict planetary orbits with extreme accuracy, calculate the force of gravity on any object, anywhere in the universe, understand how comets move, why the tides rise and fall, and how to send rockets into space. Even today, when we launch satellites, space probes, and rovers to Mars, we still use Newton's equations to guide their paths. Without Newton, there would be no space travel, no modern physics, no understanding of gravity as we know it today. His work was the bridge between the Renaissance and the modern scientific era, and the foundation for everything that came next. The legacy of Newton. Newton's discoveries changed the way we see the universe. He showed us that the cosmos is not ruled by mystery or magic, but by precise mathematical laws. Gravity is the invisible force that shapes everything, from falling apples to the orbits of galaxies. The same principles that govern motion on Earth apply everywhere, from the smallest particle to the largest star. Newton's ideas didn't just explain the past and present, they paved the way for the future. Because once we understood gravity, we could begin to defy it. We could build rockets. We could leave Earth. We could explore the stars. And it all started with a single question. Why does the apple fall? The discovery of Neptune and the power of mathematics. For centuries, the planets in our solar system were discovered the same way, by looking up. Ancient astronomers saw Mercury, Venus, Mars, Jupiter, and Saturn with the naked eye. Then, in 1781, Uranus was discovered through a telescope. But Neptune? Neptune was different. It wasn't discovered by sight, but by mathematics, predicted before anyone had ever seen it. Tonight, as you drift into sleep, let's explore how a mysterious force in the cosmos led to one of the greatest discoveries in astronomical history, and how it proved that sometimes the universe reveals itself not through what we see, but through what we calculate. A planet that shouldn't exist. The year is 1821, and you are an astronomer in Paris, carefully recording the movement of Uranus, the outermost known planet in the solar system. But something is wrong. Uranus isn't moving the way it should. According to Newton's laws of motion, the planet's orbit should be predictable and exact. But instead, Uranus is drifting slightly off course, as if something invisible is tugging on it. At first, astronomers believe it might be a mistake. Perhaps their measurements aren't precise enough. But over the years, they see the same thing. Uranus is being pulled by something unseen. Is it an unknown moon? A flaw in Newton's equations? Or something even more incredible, another planet lurking beyond Uranus? For the first time in history, astronomers realized that they might be able to discover a planet without ever seeing it, predicting the impossible. In the 1840s, two brilliant mathematicians, Urbain Le Verrier in France and John Couch Adams in England, set out to solve the mystery. They used nothing but mathematics and Newton's laws to calculate where an unknown planet should be, based on how its gravity was affecting Uranus. Imagine that. They had never seen the planet. They had no telescope powerful enough to find it. Yet, through math alone, they predicted its exact location. Le Verrier sent his calculations to Johann Galle, an astronomer at the Berlin Observatory. Galle pointed his telescope to the spot where Le Verrier said the planet would be. And there it was. On September 23, 1846, Neptune was seen for the first time, almost exactly where the calculations had predicted. It was the first planet in history to be discovered not by observation, but by mathematics. This was revolutionary. It confirmed that Newton's laws of gravity applied even in the farthest reaches of the solar system. It showed that mathematics could reveal new worlds before our eyes ever could. And it proved that sometimes the universe speaks in numbers before it speaks in light. What Neptune taught us about the universe. The discovery of Neptune changed astronomy forever. It showed that our solar system was still full of secrets. It proved that Newton's laws could predict things we hadn't even seen. And it inspired astronomers to search even further into the unknown. If Neptune had been found through math, what else might be waiting to be discovered? That question still drives astronomy today. The legacy of Neptune's discovery. Even today, we use the same techniques that found Neptune to search for planets orbiting distant stars. We measure the tiniest wobbles in a star's movement, looking for the gravitational pull of unseen planets. We detect the slightest dimming of light, signaling a planet passing in front of its sun. And we ask the same question Le Verrier and Adams asked nearly 200 years ago. What else is out there? Neptune's discovery was more than just finding a new planet. It was a reminder that the universe is full of mysteries waiting to be solved, that sometimes The greatest discoveries aren't made by what we see, but by what we know must be there, and that even in the vast, infinite darkness of space, mathematics can light the way.